Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage, and this video is going to take a look at the C++ Standard Template Library Double-Ended Queue class, otherwise known as a Deque. And so we're going to take a look here, and so I already have Visual Studio set up on the left-hand side, I've got CPP reference set up on the right. I also am using the Nikolai Jasudis C++ Standard 2nd Edition textbook. Like for this class, this is this book, the Jasudis book, is a very good resource for a better understanding of what's going on. Not that the internet doesn't supply that as well, but I like the simplicity of the Jasudis book when it comes to these kind of topics. Okay, so what is a double-ended queue? And so, I mean, it already kind of discusses what it is in its name. And so this is a distinct data type. This is not a collection. This is not a vector. This is not a stack. This is not a queue. This is actually its own data type, completely separate from all the others. That's why in the Jasudis book it's in chapter 7 and not chapter 10 or 11 or wherever the stack and the queue are found, because this is basically a foundational data structure. The stack and the queue use a double-ended queue as a default data structure under the hood, adapt to that need. So, so a double-ended queue, Deque, it is pronounced Deque, I'm not just making that up, is an indexed sequence container that allows fast insertion and deletion at both of its beginning and end. So it's like a vector, but it's not. That's kind of where we're getting at here, because you hear the queue part of this, the double-ended queue, but you're going to see here that we can actually access a lot more like a vector than we can for the stack or the plain old regular everyday queue. So we can insert and delete at both ends, and so when we do insert and delete at both ends, we never invalidate pointers or references. That's a big deal when you're adding and deleting from collections. A lot of the times, especially if you're making things larger, like the pointers that are pointing to certain memory addresses can be invalidated, because if I have to add elements to a vector and then it has to move the vector into a larger space, all the pointers that were pointing to the old memory are pointing to dangling pointers. They're pointing to nothing. And when you try to use them now, you will crash your program. So you have to watch out for that sort of stuff. So it says that as opposed to a vector, remember a vector is just a very smart array. It's just a more modern dynamic array. So because of that, the vector is one contiguous block of memory. But it says here that the double-ended queue is not. It says, and you can see that very distinctly in the textbook, where it basically shows you that there are contiguous blocks of memory, but it's more than just one large one. It's broken up into separate chunks. So it actually takes a little bit more effort if you're like, give me the 9th element inside of a double-ended queue. It takes a little more effort to do that, because it has to figure out exactly which of the memory units to go to, and then work it down a second time to figure out inside of there which element do I want to find. So let's see, anything else that's important to read offhand here? Now just say like everything else, everything automatically expands and contracts as needed and things like that. So like pretty much standard stuff. Let's see. Expansion of a double-ended queue is cheaper than vector because of the reasoning. Because with a vector, if I want to add to the front of a vector, that means that I have to push everything over. But for a double-ended queue, if I'm going to push to the start, I don't have to do any extra work. I just kind of add in it, and because I'm maintaining pointers to the front and the back, I can add to the front and then shift the pointer over, as opposed to taking the entire data structure, shift it over, and then pop the one element into place. Okay, so getting it going, pretty simple stuff. std : double-ended queue of type int. Just make it of A. That sets up the basic stuff. They say I'm setting this up so the T data type is what goes in the angle brackets here. Again, it could be an int, a float, a short, you name it. Anything Cartesian coordinate, anything that you create, could be any data type whatsoever. Pointers, you name it. The sky is the limit when it comes to that. So any data type can fill in as T. So as you notice here, if you're looking, especially if you watch the queue video and the stack video, there's a lot more here. It's not as complicated as the vector, but maybe it is. It's very similar. They say different data structure under the hood, but because it's standard and it's templated and it's a library, that you can see that these two things share a lot of similarities, especially with the syntax and the API calls. So for the constructor, this is how I can set up, like everything else, this is how I can set up a blank empty double-ended Q, and then I can set up and I can use the initializer lists for these guys. So I can go ahead and do that. I can say double-ended Q C equals B, and again, this uses the copy constructor. And so again, another time the copy constructor gets called because C is being constructed in this line of code. C does not exist at this moment in time, but B does exist, so B is being copied into C, so it uses the copy constructor, as opposed to this. Again, at this point in time, C and B are both constructed and fully available by my program, so this would use the copy assignment operator instead. So let's see. So what have we got? We've got copy constructor, we've got normal constructor, we have initializer list. Does not seem to be anything else here. I'm not in my screen. Yep, there is. Oh, actually, I can use, since this is not the regular Q class, I can say, let's try it out. I can try something like this. I can use iterators. Let me just make sure. I'm going to rebuild all and just see. So far, yep, syntactically everything is fine. So I can actually use iterators to initialize an array, or I'm sorry, a double-ended Q. So begin and end. So this basically says, give me every element of B. I mean, I'm doing the same thing as a copy constructor, but I can also do -2 or something like that. Like, I can use these kind of iterators. I can actually subtract off and add and do all sorts of crazy stuff like I couldn't do before. Like, I cannot do this in a Q class for sure. So let's see, is there anything else? I think that's pretty much it. If I'm missing one, I'm not doing the move constructors or anything like that, but here's the initializer list, here's copy constructor, here's the iterator method, and here's just plain old double-ended Q. Oh, and so I think I can also do, let's try it out. Take this one. Can I set up 10 elements? I'll make it E. And then can I do that and set up and say what? I just want everything to be 44. Does that work? Let's see. Nope, well, let's see. Let me actually fix the syntax. And let's see if that works out. Build, rebuild. Okay, run that. Oops. Run this again. Oops. Run this again. So A is empty, size 0. B has size of 5. Allocator, all the elements 1, 2, 3, 4, 5 under the hood. C, 5 elements, 1, 2, 3, 4, 5. D, 3 elements, because I was going from here to this -2, and so this will actually give me 3 elements. Because remember, end is always one. The iterator for end is always one past the last element. So if I go, if I'm going from begin to end, I go begin, and then I hit this, and I come to here and end. So I'm going to print out 5 of them. But if I go back -2, I'm going to the 4. And as long as I don't approach it, so 1, 2, 3, so that's how it ends up being a 3 size. Oops, I'm sorry, D, because I went back 2. So 1, 2, and 3 come in fine. E has 10 sized elements, all of 0. 0 is the default here. F has size 10, everything set to 44. So, quite a few different ways to construct one of these double-ended Q classes, as you would expect. All right, so moving on. Already talked about the assignment operator here, copy assignment operator, the equal operator. We do not ever have to explicitly call the destructor, so we never have to worry about that, but of course it does exist because it goes in and deletes all the memory that this thing was using under the hood that we never even really paid attention to. But other than that, a lot of this stuff now comes along. If you're a master of the vector class, or you know how arrays work, you know a lot about what we're doing here. So let's see. If I wanted to get an element, I can say int g equals d, and I can use the square bracket operator. Let's say give me the second element. So that'll give me the 2 out of this. I'm sorry, that'll give me the 3 out of this thing. Because remember, this thing is 3 sized, and so 1, 2, and 3. So this is element 0, this is element 1, this is element 2. So it would actually fill in the 3 there. And remember here that this operator does no bounds checking, but the at function does. So this will throw an exception that I can catch. So if I go outside of my bounds, I can use a try-catch block. And now it hits an oops because I'm trying to access element 6,662 out of this thing that only has 3 elements. But if I try this with this instead, just the regular old square brackets, I've crashed. You'll have to see it over here. Complete different behavior. This is it hit a debug assertion. Assertions are completely different than exception handling, and there's no way out of this because it crashed, right? So yes, if you probably want to use the at function since they both do the same exact thing. Okay, outside of that, I can use front and back to access the element, and let's see, does that return a reference? Yep, they return references. Remember how that all works? I've shown this in a couple other of my videos here. So if I want to get int g or int reference g equals f of 0, and then I can say g equals 98. Now this is where things get interesting again. Oops, let me put a breakpoint in. So I can say, okay, G is 98, but what is my F array, or my F double-ended cube? Look at that, right? Because it's now a reference. A reference is a memory address. So I was saying that let me hold on to the memory address of the first element in my double-ended cube named F, and then my next step says, why don't we change that to 98? So there you go. There's the 98 inside of there. But again, all I have to do is eliminate that one little ampersand, and turns the int reference into just plain old integer. And now that behavior does not exist because this makes a copy of this value, puts it into G, and so the G value itself is not a memory address, it's a completely different variable, so everything is 44 here. Huge difference between references and value types, and then we're not even talking about pointers or anything like that. And so the same thing applies for front and back. No, we haven't even done front and back. I was just showing about how to do this. So if I did f.front, it's the same deal. Sorry, got sidetracked thinking it out, just coming up with that. So the same deal applies. If I get the front element, it's 44. If I do it as plain old int, it saves it as 44. Oops. But if I make it an int reference, I will again turn that first element of f into 98. Okay, so that handles all of the element access stuff here. So now push it on through. So when it comes to iterating through, there's many ways I can iterate through. I can use the range-based for loop. If I wanted to do like a range-based for loop for every integer x that's part of b, print out the x value and then a space. Why am I getting an error? Nope, not an error. So that's one way to do things. So there's 1, 2, 3, 4, 5. There's my 1, 2, 3, 4, 5. And so, but that, so I can do that. If I want to, I can use just the plain old int I equals 0. I is less than b dot size plus I. We can use the size function for that. And I can't use x anymore, but I can use b sub I or b dot at I. This is the old way to do things. If you can help it, don't do this anymore, just because it takes, there's a lot of code here to write, and if you forget one little thing, you have a very subtle bug as you advance on with your code. But again, I still get myself to 1, 2, 3, 4, 5. And so the final step here, just using iterators, since this is the next big part here, it makes sense to try that out. So I can actually say, give me, oh my goodness, QUE, okay, of int, : iterator, iter equals b dot begin. And I can say while iter does not equal b dot end. Oh my goodness, right? All this fun stuff. Cout star iter, because I have to dereference an iterator if I want to access the element, what's stored inside of it. And then, I need an extra parenthesis here. Then of course, if I do this way, and I go, oh boy, here's my, there you go. Because that's the difference between a while loop and a for loop. The while loop it's very easy to forget that I have to go in and I have to increment my iterator, and all I have to do is do a pre-increment on this guy. And then this will print out 1, 2, 3, 4, 5 like it has for the other couple of ways that we've done it. So multiple ways to project yourself through. Say the iterator method is just one of them. And so if I wanted to, actually, I could go ahead and use a reverse iterator. Let me move this over a little bit so we can see it, which is kind of cool. So to make this work, I have to use r_begin. And I said as long as iterator does not equal r_end, I can still print out star iter and do the same thing. And it feels weird because you're still incrementing the iterator, but I'm starting at basically the last element and I'm working my way to the other into backwards. And so by incrementing, I'm actually moving forwards. It sounds like Willy Wonka thing. By moving forwards, I'm moving backwards. So I can actually print out 5, 4, 3, 2, 1 using plus iter here. But you can't, it's not as easy to do. I don't think you can do a range-based for loop where you go in reverse. And if there is, send me a comment. I'd love to hear it if there's a simple way. I just don't know just yet. Okay, so that's the basics of just using iterators for the most part. And iterators are a big deal when it comes to the algorithms and all the other setups that we can do to actually take the standard template library and advance and make it super awesome and pretty easy to use when it comes to all this algorithm stuff. Okay, so a couple more things here. So empty and size, you can imagine it's just how many elements are there in my double-ended queue. Empty just tests to see if it's 0, returns a Boolean true or false, and size just gives me the actual integer or size t value, size type value, an unsigned integer amount of elements currently in the double-ended queue. Okay, so my goodness, what more is there? I can clear the double-ended queue. So let's see. So like this printed out 5, 4, 3, 2, 1, but if I just went b.clear, now it prints nothing because now there's no elements. Begin and end are looking at the same place, so boom, nothing prints just because of the b.clear. And so you have to watch out, like anything else. If I have a double-ended queue of pointer objects that I've allocated myself, and if I just pull b.clear, it will not call the destructor on, or basically just basically give back that memory. It will not delete the memory and give it back. So if you forget that, if I had a double-ended queue of integer pointers and I newed everything up and I forgot to delete everything, I would have a huge memory leak. So you got to watch out. Clear is great and all, but you have to understand for every new, it's your responsibility to delete that information. So insert, the thing is an insert requires, oh, maybe not. No, everything requires iterators. So to use this insert function, so like, oh, I would love to be able to go in and add a 5 somewhere, maybe the 5th element here, f.insert. I have to say, okay, get me f's begin iterator, add 5 elements, and put whatever number I said I'm just going to make up, put a 9 in there. And let me put a breakpoint in here. So this takes and says, okay, before 5 elements over from the begin iterator, add a 9. So now you can see this here. It takes 0, so it moves over to, it puts a 9 into element 5 and moves everything, shifts everything over to the right. Or it possibly might shift everything over to the left. It's a double-ended queue. We don't necessarily know what it's doing under the hood. As long as it's doing what we want it to do, and it's doing it fast and efficient, we don't necessarily care how it's going about doing it. So erase works the same way. If I wanted to go ahead and erase it right back, or oh, jeez Louise. It's been a long couple of weeks, but for everybody, right? So let's see. Okay, so I put the 9 in there. So I can show you breakpoints in 2 places here. So just like before, just make sure that 9 is in there. There it is at element 5. And then now I go one more time and I erase what's at that element location, and then now it's gone and shifts everything over to accommodate the fact that I'm deleting for erasing from that specific location. Let's see, anything else? We're not going to worry about emplacements. It did erase, it did clear, swap and resize. So the last elements here, so happen to do with basically the way we could handle stacks and queues. And so because of that, a double-ended queue, I say because of the way the data structure is set up, it's very simple for us to add elements to the front and to the back. A vector, it's only easy to add to the back, and that's again because the data structure is zero element, zero size or zero size. Starts with element 0 and works its way forward, but a double-ended queue kind of starts kind of halfway in the middle and allows us expansion in both directions. So it's pretty ingenious. It's a pretty ingenious way to do things. So so if I want to get the first element or I want to get the last element, I use the front and the back element access functions that we've already used. But if I want to push from the back and pop from the back, or push from the front or pop from the front, that's how we go about doing that. So just to kind of finish up here and say, okay, I'm printing out every element. I've got all these different elements. Let me just copy, well, here, let's just do one more big example showing here. So I'll say, I'll set up a new double-ended queue. Well, I don't know what that is. Control Z, oops, Control Z, Control Z, Control Y. Okay, so give me a new double-ended queue. Let's put a few elements in there to start. Let's just put a 5, an 8, and a 2. I'm just putting a few. I'm just making stuff up random here. So now what I want to do is I want to say, give a for loop and say for every I equal to 0, I is less than 5 plus I, p dot push front I. And then let me do this one more time. And then say let's push to the back. And instead of 0 to 5, why don't we do 6 to 9? I don't know. So then let me do the range-based for loop for every integer I that is part of this P. Print I with a space. Okay, so let me just comment this print statement here so we can kind of so we can focus on just what I'm doing right here at the end here. So let's take a look what pops up. Oops, I have my breakpoints. Boink, boink. So there we go. So what do we have? I was saying we're pushing to the front. So you might even be like, oh my goodness, I'm adding 0, 1, 2, 3, 4, 5. But every time I'm adding, so 5, 8, 2 was the start. But then I'm like, hey, add a 0 to the front, add a 1, add a 2, add a 3, add a 4. So the 4 actually comes first. 4, 3, 2, 1, 0, 5, 8, 2. And the same goes for the back. If I'm going to insert 6, 7, and 8 in order, 6 goes first, then 7, then 8. So that pushes to the back every single time. And so again, we proved, or we can show that if there are no elements, right? If we are, just in case we already did this, if I do give me a.front, the thing crashes because I have an empty double-ended queue and I'm trying to get, by reference, I'm trying to get the value that's at the front, and it's going to completely crash on me. So I have to make sure, if I'm going to be popping off things or accessing elements at all, I have to make sure that that element exists. So so I'll do this one more time here. Or I'll actually put this in a for loop here. So while, actually, should write a function for this, but too late now. So while p.empty equals false, what will I do? I'll print the whole thing out. And since I'm here doing this, I'll print an end line, because we're going to print this out over and over and over again. So then, oops, ST::. And then I'll say, okay, so how about I print out everything, or before I do that, how about I do p.popback? So I'll take everything off from front to back. And oops, I have an error here. I don't have the closing curly brace. So what happens now? Well, what happens now is I don't have the C out in the right place. And that's not in the right place either. I hate it. I'm sorry, I'm not trying to confuse anybody. Put the print there outside of the inner loop. There we go. So now you can kind of see what's happening. So I'm printing out the master list like we did before, and now every single time I'm just popping off the back. And so and then I'm printing out the whole double-ended queue one more time. So then when I finally kick the 4 out, the thing is empty, so it falls out and kicks out of the loop. So it doesn't print that there's nothing there. So the same would go if I wanted to do pop front. And it just goes in reverse, because every time I'm doing one of these things, I'm popping off the front, and then everything else is shifting accordingly. So there you go. So we have this data structure. Say vector is good, but sometimes double-ended queue can be better. It all depends on the situations. If you're just trying to use a quick and dirty array, use a vector. If you're trying to have a lot of, if you're adding and removing a lot of elements, and you can't just use a normal queue or can't use a normal stack or something like that, this is a great way to go about doing things. So that pretty much covers everything I wanted to cover about a double-ended queue. As always, throw me a comment, a real comment, and ask me a question if you have anything about this lecture. Otherwise, send me an email. And thanks for sticking up with this, and we'll see you next time.